So in this video, we're going to talk about a very common type of reaction, and that is combustion. So combustion is pretty common in the chemical world, happens all the time, used in a lot of industries, so we want to make sure we understand that, and especially how we can analyze and work with these type of reactions. So combustion in its general sense is the reaction between a fuel and oxygen. And that can be many different types of fuels. So I list here a bunch of different type of reactions where the fuel is reacted with oxygen. It could be pure carbon. It could be some organic molecules, whether it's C3H8 or CH4 or whatever, any sort of organic hydrocarbon molecules that are made of carbon and hydrogen, although there are many other type of molecules, organic molecules that could be reactants, fuels. Here we have CS2, etc., etc. Whenever we react something with oxygen like this, we call this a combustion reaction. And there are many advantages to why we want to combust something, but probably the biggest one is it produces heat. If you've ever sat around a campfire, or maybe you have some sort of heater in your house, it produces heat, and we use that heat energy. We might use that heat energy to stay warm. We might use that heat energy to drive an electrical turbine to produce electricity. Various different uses of it, but again, the generation of heat is one of the big reasons why we combust things. So there are two different types of combustion. The first one is complete combustion, second one incomplete combustion. And more or less, complete combustion is the formation of CO2. Incomplete involves the formation of CO. So here is two different reactions where it's reacted with oxygen. Neither of these reactions are balanced here. We could go through and balance them. But in this case, we produce CO2 and water as our main products. In this case, it's CO and water also for the products. This is complete combustion, incomplete combustion. Generally, combustion, we prefer it to be complete, but we may have some of our reaction taking place where some of our fuel goes through a complete combustion reaction route, and some of our fuel goes through an incomplete reaction. So we just got to keep that in mind, because as we're dealing with problems, sometimes we may deal with complete combustion, sometimes we may deal with incomplete combustion. The other point we need to talk about is oxygen. Where is it coming from? So when we react something or combust it, we could react a molecule or some sort of fuel with pure oxygen. We could take pure oxygen, react it with the fuel to combust it, but that's not typically the case. The more typical case is we react it with air. So we have air reacting with that fuel. Again, if you are burning some wood on a campfire, your source of oxygen comes from the air. You're reacting that fuel with air, which is a mixture of oxygen and nitrogen. And really, this is one of the big reasons why we use air, is it's cheap and readily available. If we wanted to react something with pure oxygen, we would have to separate oxygen from air or from some other source, and that costs a lot of money to produce that pure oxygen and then to go ahead and combust it. There may be certain cases where we react something with pure oxygen for very specialized cases. For instance, on a space shuttle, where space and weight are limited, so they may use pure oxygen for combustion on a space shuttle or some sort of specialized application. But for the most part, we just use regular old air to combust things. And these are the typical properties that we assume of air. Air is a mixture of nitrogen. Air has some oxygen, nitrogen, argon, neon, a bunch of other molecules running around, floating about, depending on the location and what the air quality is, pollution and so forth. But we typically ignore everything but oxygen and nitrogen, and we assume that we have 79% nitrogen, 21% oxygen, or in other words, we have 79 moles of nitrogen per 21 moles of oxygen, or 21 moles of oxygen per 100 moles of air, or 79 moles of nitrogen per 100 moles of air. So this is the typical composition: 79 mole percent nitrogen, 21 mole percent oxygen, and the average molecular weight given here for air. So when we're dealing with these combustion problems, we need to remember how we need to take into account that air is a mixture of oxygen and nitrogen, and typically this nitrogen does not react. So if I have some air coming into a reactor, I have to take into account that some of that air is going to be oxygen, and we could calculate how much oxygen is coming in and reacting with our fuel. But we also need to take into account that nitrogen part, which is the majority of air, is just going to go right through our reactor and not going to react. So the other thing we need to talk about for combustion problems is oftentimes we talk about the basis, and the difference really is there's a wet basis and there's a dry basis. And wet basis is the composition taking into account water. Dry basis is the composition ignoring water. And it's dry because we're ignoring any sort of wet component, the water component. So for instance, if I have 2 moles of nitrogen, 5 moles of oxygen, 3 moles of water, and I wanted to know the composition on a wet basis, that would just be taking into account all 3 molecules, all 3 components. So this all adds up to a 10 moles right here. So 2 divided by 10 is a mole fraction of 0.2 for nitrogen. 5 divided by 10 is a 0.5 mole fraction of oxygen, and 3 divided by 10 gives me a mole fraction of 0.3 for the water. So we just sum up all the total number of moles, take in each individual component, divide it by the total number of moles. The dry basis mole fraction ignores all of the water. So in this case, if we ignore this, go ahead, scratch that out. If I go ahead and ignore that, then I only use 7 moles for analyzing the composition. So 2 divided by 7 would tell me the mole fraction of nitrogen, and that's 0.29. 5 divided by 7 will give me a mole fraction of 0.71 of oxygen. And again, we just have to specify oftentimes whether our composition is a wet or a dry basis. If it's not specified exactly, then we can usually just assume it's a wet basis, but you may have problems where it tells you that this is the dry basis composition, and you just need to remember that that means ignoring water. So the next concept we need to deal with is the amount is theoretical oxygen and theoretical air. So let's just look at an example here. We have here methane, CH4. And to calculate the amount of theoretical oxygen, we assume that all the carbon forms CO2 and all the water forms H2O. So the final products are CO2 and H2O. So if I write out the balanced equation, this is what I get. Methane plus 2 molecules of oxygen reacts to form CO2 plus 2H2O. So let's just say I start out here with 100 moles of methane. Well, the theoretical oxygen is the amount that would be to completely react away all of that methane. And if we just look here at the stoichiometry here between oxygen and methane, I know that the theoretical oxygen has got to be 200 moles, because that's how much would be required to completely react away 100 moles. We would require 200 moles to completely combust 100 moles of CH4. And that's it. That's the theoretical amount of oxygen. The other part to this is theoretical air. How much air do we need to have complete combustion of our product, or of our fuel? So if I know the theoretical amount of oxygen, I can calculate the theoretical amount of air. So in this case, if I have the theoretical amount of oxygen is 200 moles, continuing this example up here, the theoretical amount of air is how much air do I need that will supply 200 moles of oxygen. So I need an air that has 200 moles of oxygen within that air. And so this is where we use the mole fraction, or the ratio here. So I have 200 moles of oxygen I need, and I know that for 100 moles of air has 21 moles of oxygen. So I can go ahead and just plug this out here. And if I just do the math here, that means my final result, the theoretical amount of air, is 952.4 moles of air. So this is the amount of air I would need to completely combust 100 moles of CH4 or 100 moles of methane. And that's the concept of theoretical oxygen, theoretical air. How much do we need to completely combust something? One more concept here, final concept in dealing with combustion, and this is similar to what we've dealt with before. So excess, we have a limiting reactant, we have an excess reactant, and excess air is just the amount of air which exceeds the theoretical amount of air. So just like we can calculate how much excess we have, the fractional excess of an excess, the reactant that's in excess, or the percent excess, we can do the same thing for air. So continuing on with the example we had earlier on the previous slide, we had 100 moles of CH4, which has a theoretical amount of oxygen for complete combustion of 200 moles, again according from the reaction equation, which is equivalent to 952.4 moles of theoretical air. Again, this is how much air we need to completely combust CH4. Now let's just say we have 1200 moles of air. That means we have more moles of air than we need for the complete combustion. We have excess air. So we can calculate the percentage excess simply using this formula right here, 1200 minus 952.4, all divided by 952.4, multiplied by 100, gives us 26% excess air. And we could also calculate the fractional excess air. Fractional excess air would just be without the 100, so fractional excess air would be 0.26. Same concept as we had before when we're dealing with excess, whether it's percentage or fractional, but in this case we're calculating it of air when we have a reaction.